Hello everyone, I am Shivani Rajput. So let's get started the circuit composer video in continuation of my last video. So yeah, let's get started. So this is the kind of dashboard as which we have discussed in my last video, and let's click on this tab launch composer. So yeah, um, this will let you open to this particular circuit composer view that you see here, and you have all the codes that you have run so far. And for someone who is joining for the first time, will show no files there. So this is the place for actual circuit composer. You have the set of operators, gates, and you have their circuits. So as soon as there are also a couple of things in the file menu. You can drop down, you can make a copy or delete, you can edit a particular quantum circuits. You can edit, you can clear the circuit, you can edit it. And you can, if there are a couple of operations running, if there are a couple of operation running, so inspect button would get activated, and it will provide a step by step debugging of a circuit. And we can see step by step where something went wrong. Okay, so here is the view tab. It will give you the graphical editor, state vector, probability, q sphere, the code editor, which we all see here, the graphical editor, the code editor, the probability, q sphere, state vector, all these thing here. In the view tab there is one thing, that is q sphere, which we see here. I want to discuss one thing. There is one thing, in a block sphere, and here it is q sphere. So block sphere is particularly when we are working more than for more than one qubit. Whereas Q-sphere will give you the state information of a single qubit, and multiple qubit, including the phase angle. So you can see here the phase angle and the state. Okay, so yeah, uh, yeah, actually, yeah, we can see here. And now you can go on the view, you can see the code editor. So whatever you drag and drop and create, it will automatically create a corresponding code in the cascade, and also in the quantum assembly language. So wherever we are comfortable, we can directly open in quantum lab and use that programming tool as well, so any circuit can drag and drop. So this measurement probability view that you see here gives you the expected measurement probability and the result of the quantum circuits. And it is also downloadable in various formats. You can click in here and you can see it's download, it's you can download it as png or pdf and many much more. So for the vector state vector, it will allow you to preview the state vector result of your quantum circuit. So the state vector view gives you the computational basis on the x-axis and the amplitude on the y-axis. And so that's the two different thing here, probability and the state vector. Amplitude is here, and here is the probability in the first graph. And we'll be using the quasar simulator, which will gives you the count, and also using the state vector simulator that will give you the state vector representation or the amplitude. So let's hit our new file. Okay, it's already there. So yeah, let me name this. Suppose we'll be discussing first single qubit gate. So let me name this. So let's try to run it on a hardware computer. So whenever we click on the new file, it will default give you the three qubits class quantum qubits. Wires, you can see here the wires out of this register are in the compact notation, so where we can see them all together. And in a quantum register, all these are the separate wire running out. So we are focusing on the single qubit. So let's delete the other two qubits. And yeah, so let's delete the other two qubits. And this is the classical bits where we going to store the measurement result, because once we measure quantum state as something, quantum state actually falls into the classical states of 0 or 1. So yeah, we measured it classically. We can notice here all those quantum bits initialized to 0, you can see here. One important thing is here, there is one, criteria, that is DiVincenzo's criteria. So according to that, quantum circuit must be, initially be initialized to 0 or ground state. So yeah, we will drag or drop the operators. So not gate, as we have not gate is the, we can drag and drop the operators here. We can drag the not gate, it is the there is a single qubit gates, which is the, not gate, poly x y and z, poly x y z gate. So we can drag and drop the not gate. We can see uh, here, yeah. So like suppose, wait, let me delete this. Let me delete this first. Let me measure the qubit, right? As I was discussing it, initially should be in the ground state, on the 0 state. We can see here that, yeah, it's showing the probability of 100% for having it in the state 0, or here also in the state vector it's having the amplitude 0 with the phase angle 0. Okay, for more clarity, let me yeah, remove this code editor part. So yeah, we can easily delete this. So yeah, there is a single qubit gates, like, which is the NOT gate, the poly X, poly Y, poly Z gate. So I am applying a NOT gate on the qubit quantum bits. So yeah, so quantum operator initialized to 0 now. So q0 would be 1 now after applying the NOT gate. That's what we see here in the result, with a 100% probability in the state 1. And this in the q sphere we can see it, we can see that there is a counterclockwise rotation of the vector from, 0 to state 1. And so yeah, we can notice that not gate worked probably, it was able to move the state from 0 to 1. Also the quantum sphere we see here, we can see that there is counterclockwise rotation. And yeah, so how do we run this? We can click on the right setup and run. There are the hardwares, there are so many. We can see here the simulators and the hardwares that are available to you. I want to choose the IBM Quasum simulator, and we can decide the number of shots, basically number of times we want to run the particular, circuits which we have made. So one more thing, that here I've set it to 1024. It's not necessary that we have to put it only to the power 2 to the power n power of things. So where n is the number of bits, we can have any number. We can run up to 8,000 times or of the same circuit to get the measurement probabilities. So I'll be doing it on 1024. Now let's choose and run it. We can see here the notification. Okay, sorry, I forgot to measure it. We need to measure, then only it will work. So yeah, run. So we can see here the notification job sent to IBM Quasum Simulator, and it will also end up with the notification that job is done. We can check there. So yeah, it will take a little bit time. Yeah, let me discuss one thing. We have noticed, one thing, just wanted to put this, like, hardware, the processor are in the name of, birds, which we have discussed earlier in the first video and the second video also. The canary, eagle, hummingbird, and this actual quantum computer is on the name of the city location, which you can see here, like, IBM Q Santiago, or IBM Q Belém, and all this. So this is not like it does not mean that there is quantum computer in that particular city. It simply means that there is quantum computer. It simply means that there is IBM offices there. So okay, so we can go there in the tab composer. Let's check whether it's completed. Okay. Oh, something went wrong. What happened? Let me try it again. Okay, job 121024. Run. Jobs and to IBM Q Quasum Simulator. Let me check. Yeah, it's completed. Okay. Yeah. Here we can see the result. So outcome is 1 with the frequency of 1024. So it's 100% times outcome was 1. So that's the kind of thing which we have which I was discussing, and we have run it on actual simulator, so we can tally the result. The both are get we have from both the side we are getting the same result. So yeah, now for more details we can click on this, and yeah, we'll open the new terminal. Yeah, here we can see the status timeline, how long we have to wait in a queue, its total running time, or, the several other things we can see here, moving up and down the diagram, the cosm, the simulator, and all. We can see several other things, several more details here. So, yeah, moving back. Okay, let's try slightly different circuits. So now hit a new file, and I want to discuss, let me edit this. I want to discuss the superposition. Here will we use Hadamard gate, which is a single qubit gate. We can drag and drop it down, and that we use to put the qubits to our superposition. Now, one thing I need to discuss is the nomenclature of qubits. So you can see here 000 001. I want to discuss that the rightmost qubit which we see is the q0, represent q0, then q1, and the leftmost qubit represent q2 according to this bits. So yeah, there are three bits. If we delete qubit, it will become, yeah, z q0 and q1, then it will show only two qubits. So yeah, q0, here q0 becomes hmm, let me delete one this single qubit gate. Yeah, so yeah, we can understand this particular Hadamard gate able to put this qubit into up in the setup of 0 and 1. So this is a probability of 50% chances of having this in state 0 or in the state 1. We can see the q sphere diagram also, a zero point 0.5 probability in the state 0 and the zero point 0.5 probability in the state 1, and the state vector representation also. So we can see the state vector graph also. Here is the probability amplitude is 0.707, and there are several other background calculations. So it's because of 1 by root 2. Qubit initially was in the 0 state, and after applying Hadamard, it is in the state of 1 by root 2 cat 0 plus cat 1. So okay, let's put the measurement operator here, right? Okay, so we can see one thing, that in the if we create add the code editor, we can see Qiskit the create the to create its own code here, whatever we are dragging and dropping. So then we can go on the setup and run it on actual simulator. So yeah, the same IBM Cosm simulator I'll be using, and the same number of shots, and run. Yeah, it will show the notification job sent to IBM Cosm simulator, and yeah, let's wait. Okay, result is there. New job result. Okay, wait. Okay, we can tell you the time right now, 8:36. Yeah, this is the result. Okay, details. Yeah, superposition. This is the result. Here we can see the frequency 505 of outcome 1, and 519 outcome 2. Almost the same frequency, almost the same frequency. So we are getting the correct result according to this. So okay, let's explore the third principle. Okay, let me hit to the new file, and that third principle is the entanglement. Okay, rename it. So it involves the use of multiple gates, qubit gate. Okay, so C naught is a multiple qubit gate. It help in creating the entanglement. So first we have to do is that we have to initialize to state zero. So let me just remove one qubit. Okay, yeah. So we are not looking at three qubit gates. So at this point of time, we just drag and drop the gate on quantum Q0. So we are just creating the superposition on Q0. Then what we can do is we can drag and drop the C naught gate. So first let me put the Hadamard gate on Q0. It will create the state of superposition like 50-50% probability in both this state. We can see here. And there is by applying then we'll be applying C naught gate. It will entangle the qubit 0 Q0 and Q1. C naught gate basically works. There is one source qubit and one target qubit. So here Q0 is the source qubit and Q1 is the target qubit, and it actually entangles the Q0 and Q1. How do we actually know whether we have created entanglement property or not? We need to measure both of the qubits, Q0 and Q1. Okay, so okay, we can see there is 100% probability chance. Okay, so now let's see, go there to set up and run, and we can go there and run it on actual simulator with the same number of shots. We'll run it. Job sent to IBM Q Quasm simulator. Let's wait for the result. It will give you the notification, job done. Okay, it's taking little time. Okay, we can go there and check whether it's completed or not. We can click on the job. It will show us yeah, it's showing the status that it's still running. We can see all these things right there. So yeah, okay, one thing I want to discuss is that there is two things: there's superposition and the entanglement. So superposition is basically the state of the qubit being in the both, the probability of the qubit being in the both state, it does is 0 or 1. And entanglement will give you the, when we measure it, it will end up with having in the one state, either in the 0 or in the 1. It's still taking time. Okay. Okay, new job result is there. Okay, completed. We can see here the result. Okay, there is some glitch. Okay, it's showing 100% probability. There might be some glitch here. This is the perfect result. We can see. Okay, yeah, this is the perfect result. Like they are entangled with the closed qubit frequency 510 for 00 and 514 for 11. So yeah, as we have learned entanglement, we want to really go to the Bell state. So yeah, let's hit to the new file, name Bell state, rename it to the Bell state. In the theory, we have read that it's basically a maximally entangled state. We can actually do this in this particular example. So, but no problem, for more clarity, that entanglement example. But no problem, for more clarity, we can hit to a new file. So yeah, okay, let's do different kind of measurements on Bell states, because we have already know what is entanglement. We have already have fair idea about it. So first we need to create an entanglement. So we need to decrease one qubit here. So for superposition, I need to add Hadamard gate on first qubit, and then C naught gate on the to entangled Q0 and Q1. Yeah, you can see here the probability of 50-50% of having in the state 00 or in the 1 1, both the qubit together in the state 0 or in the state 1. Now let's measure it. Yeah, we can do this. Okay, this is the bell state. Let me run this on the Quasm simulator by hitting the setup and run. I'll fix it to 1024 shots only, and I'll run it. Job sent to IBM Quasm simulator. Yeah, new job result is there. So we can see that it's showing the exact right result of 50% chance of being in each of the states. So we can see result is random, half of the time q0 in the state 0, and half of the time it's in state 1. So yeah, okay, let's try to measure it on in our superposition basis. So all you need to do is just to remove this measurement thing, and yeah, you need to add header mart gate. So after c not gate, header mart gate on q0, and yeah, and again q0. So now wait, and q1, and measure it. Wait, actually apply header mart gate on. So now q0 in the superposition, and we'll run it on Quasm simulator. So okay, we want for perfect correlation. How do we do that? Actually remove the measurement and header mart on q0 and q1. So we measure both of them. Yeah, measure both of them, and yeah, let me send this job to Quasm simulator. Okay, send job, and job new result. Okay, wait, let me check it. So this is the result. Details, yeah, bell state, correct. So yeah, we can see here that probabilistic we see certain type of noise. So okay, no noise is there. Yeah, certain type of noise, because there is frequency changes is there. So yeah, if q0 is measured in the state 0, we know that q1 is in the this state as well. So they are always in the same state. So that's why we are called them maximal entangle state or bell state. And which is this, we would actually go back where we see yeah, wait, yeah, we see the circuit composer dashboard. Wait, yeah, here is the result. We can see the result. So let's try all these things in Qiskit by applying the codes. Here we were dragging and dropping the circuits, and the code was automatically generated in the code editor according to what we are doing, the operation here. And in the Qiskit we have to create we have to build this code by ourselves to get the circuit. So let's get to in the next video. So yeah, thank you.